Okay, so welcome back to Mind Mentors. Today we're going to solve this problem from the 2014 qualifying round of the MIT for the MIT Integration Bee. Again, looking at this problem, this is problem number 13. It looks a little complicated, but it shouldn't be too bad if we know some basic properties of integrals and some basic techniques of integration. So when looking at this problem, the first piece of idea that came to my mind was using integration by parts, and here's the formula by parts. Again, this formula is very easy to prove. You can, I encourage you to try it out by yourselves. It's just basically the idea is that it's just a reversal of the product rule, and it's not too bad to prove. So again, here's just the formula, and we'll just be using it to solve this integral. So first of all, I can say that the integral right here, I can separate it by the linear property of integrals. So I have the integral of e to the x. Again, log is just ln. They really mean ln. So e to the x ln 1 plus x squared dx minus 2 e to the x 1 plus x. Again, tan inverse x is just tan arctan x is just tan inverse x dx. And e to the x ln 1 plus x squared dx. And we can see that the inside function right here can be represented as u prime times v. Again, what do we want to integrate? What's easier to integrate? ln 1 plus x squared or e to the x? ln 1 plus x squared is quite, it's not easy to integrate as compared to e to the x. So in our case, we'll choose e to the x to be u prime. So if I choose that, I can simplify this as follows. This becomes e to the x, integral of e to the x is just e to the x times ln 1 plus x squared minus. Again, now I'll just take e to the x. And if I do the differentiation of ln 1 plus x squared, the differentiation of ln of any function is just 1 over that function times the derivative of the inside function. So it's 1 plus x squared multiplied by 2x. I'll just write 2x right here. Oops. So 2 to the x dx. Okay, so now I can simplify this integral right here using a similar technique. So I'll just expand the following integral, put the minus there. Integral of 2 e to the x tan inverse x plus the integral of 2 x e to the x tan inverse x dx. So I'll just rewrite the following expression. If I look at the inside function, it is very similar to the outside function that we had right here. So since it's very similar to the outside function, I'm just going to integrate it using a similar strategy. Well, the integration, I guess, is just directly 2 e to the x. So again, tan inverse is very hard to integrate, so instead we just chose u prime to be 2 e to the x. Minus 2 e to the x. Again, integrate the differentiation of tan inverse x is just 1 plus x squared. It's a very famous differentiation property. Okay, so this integral right here becomes this right here. Okay, great. Now we'll try to see if you can finish up this one last integral. So again, if I look back, I can recognize that tan inverse x is easy to differentiate, but harder to integrate. So I'll integrate this function right here. And if I take that to the top, the integral of 2x e to the x, again, using just by parts is just 2x e to the x minus 2 e to the x. And a way you can just sort of check that is just by differentiating this expression right here by the fundamental theorem of calculus. So we'll write this as follows: plus 2x e to the x minus 2 e to the x tan inverse x minus the integral of 2x e to the x minus 2 e to the x. Differentiation of tan inverse x is 1 plus x squared dx. Okay, I'll just simplify this expression right here. This becomes 2e to the x tan inverse x minus, I'll leave the integral as it is. Again, the integral isn't ideal to compute directly. So we'll see if stuff cancels out as we simplify along the way. So I'll just expand this out right here. 2 to the x e to the x. I'll take out the bracket. 2x e to the x tan inverse x minus 2 e to the x tan inverse x plus the integral of 2 e to the x 1 plus x squared minus the integral of 2x e to the x 1 plus x squared dx. Again, I sometimes forget to write dx by at the end of the integral, so yeah, just assume it's there. Awesome. So now we can notice that this integral right here and this integral right here would cancel, again, because this is the negative and this is the positive. So I'll just put a cross over that. So great. Now at least two integrals have canceled, and let's see if we can do something else with the expressions. So now what I'm going to do is I'm just going to simplify everything by implementing this negative inside. So I get e to the x ln 1 plus x squared minus the integral of 2 to the x e to the x 1 plus x squared dx minus 2 e to the x tan inverse x minus e to the x 2x e to the x tan inverse x, and then plus 2 e to the x tan inverse x plus 2 to the x e to the x 1 plus x squared dx. And this is after implementing the negative. And two things that you can notice is that this integral are the same and opposite polarity, so they cancel. This expression right here and this expression right here are the same and of opposite polarity, so they can cancel right here. So I can cancel the terms, these terms, and these terms. So now I think I have the answer. And one more thing I want to note is that since this is an indefinite integral, meaning that if we look back up here, there were no specified bounds of integration. So that means I have to put a plus c. Because again, if I were to reverse or differentiate the final expression, I should get back the expression on the inside. But again, I can always have a plus c on the outside, because if I differentiate a constant, since it doesn't have any rate of change, thus the derivative of constant would still be 0. Thus the expression that I would get back would still be the same. So that we include a plus c. Minus 2x e to the x tan inverse x plus c. So this is the final value of the integral. Hope you enjoyed the video, and we'll see you next time.